So to continue with Chapter 3, we're going to work with approximations to histograms. Now, when we model a relative frequency distribution with this normal probability distribution, we use the area on the normal curve to approximate the areas of the bars in the histogram being modeled. Or we can approximate proportions that are just too detailed to be computed from just the histogram. Now we're going to take a quick look at an example. This is from Health and Nutrition Examination Study from 1976 to 1980. They have the heights of adult men aged 18 to 24. The mean is 70 inches, standard deviation is 2.8. Now they say that the heights follow a normal distribution. In other words, we can model these heights using the normal distribution. And this normal distribution has a mean of 70 and a standard deviation of 2.8. So we can say, using the 68, 95, 99.7 rule for men's height, that 68% of the men's heights are between 67.2 and 72.8. Now how did we get that? Well, we found, because we know that within one standard deviation for the mean, 68% of the data lie. So we just took the mean and subtracted that standard deviation. That gave us the 67.2 for the lower end. And then we took the mean plus one standard deviation. That gave us the 72.8. And we did likewise for the 95% and the 99%. But the question can be posed in other ways. So what if they said, what proportion of men are less than 72.8? Well, we got to figure, what is less than 72.8? How many standard deviations is 72.8? Well, in the last slide, we saw that 72.8 was at the positive one standard deviation away. So how do we get that? On the slide is one way to get it, but another way, the way that I'm going to show you, is that half of the distribution, the mean, that would be 50% of the men, and we know that one standard deviation between the mean and one standard deviation is 34. That's 34%, so 34% plus the 50% gives us the 84%. So there's many different ways to figure these out. Now how are we going to figure out this? What proportion of men are less than 68 inches tall? Well, 68 inches is 2.8 standard deviations from 70. The empirical rule doesn't work for us. It only works for the integers 1, 2, and 3. So now we've got to figure out a way to do this. And what we're going to learn, that's what we're going to be learning next, is we've got to use a table to find these answers. But there's a little bit of, we have to do a couple of things before we can just go into the tables. So we're going to learn about the area under the normal curve. And as I told you, we can say area under the curve, we can say the proportion under the curve, or we can say probability. These words you'll see somewhat interchanged. So suppose a random variable is normally distributed, and it has, or we are modeling it, and our model has a mean of mu and a standard deviation of sigma. Now the areas underneath that normal curve are for any intervals of values. And they can represent either the proportion of the population with the characteristics described by the interval, or the probability that a randomly selected individual from the population will have characteristics described by the interval of numbers. So that area under the standard normal curve is a proportion or a probability. Now a point I'd like to stress here is that there is no area under the standard normal curve with any single value. So we can only speak about intervals. Otherwise, that area or proportion or probability will be 0. So we're going to find that if we said what proportion of men's height equals 7.2, we would say 0. Now I told you that we use a function to find the areas underneath the curve, and we do this by integration generally when we are learning this in calculus. But look at this equation. This is the equation of that normal density curve. It looks pretty nasty. Well, luckily we don't have to compute these areas under the curve. We're going to be using the standard normal table. And in fact, we couldn't use our normal integration to actually do the areas under this curve. We're going to use the standard normal table found in your book, Table A, or in the tables that you can download off of Blackboard, to find standard normal, to find these proportions of probability. But this table is for the standard normal distribution. And what do we mean by that? The table in the back of your book, in Table A, and in most tables in any statistics book, the table is for the standard normal distribution. That is the distribution that has a mean of 0 and a standard deviation of 1. You have what we have in our table is the cumulative proportion. So in other words, it's whatever the number is, we're finding the proportion of values to the left of that number. So as you can see in the picture, you'll have a z-value, and the entry and the z-value is to represent a value for the standard normal variable. And when we put that number in, we look in the table, the body of the table will give us what proportion would be that value or less. So in other words, what proportion of observations in that distribution that are less than or equal to that particular value. So the standard normal distribution, we're going to find the area, proportions, or probabilities under the standard normal curve, find z-scores for a given area, and interpret the area under the standard normal curve as a probability. So how are we going to find these areas, proportions, probabilities? Well, there are several ways to calculate the areas under the standard normal curve. There's no simple formula for this. We have to use the table. Or we can use technology, like our mini-tab. We can find the area to the left of a particular value. We can find the area to the right of a particular value. And we can also find the area between two values. And it points to what it would look like when we're finding it. The notation would be the probability that z is in between two numbers. That's when we have finding the area between two values. Then we have the probability that z is greater than a, represents when we're looking for the area to the right of a boundary, where the boundary is a. And then the probability that z is less than a, that's finding the area to the left of a boundary. So let's see how we're going to do this. Open your book to Table A. And in Table A, we're going to find this probability. We want to find the probability that z is less than 1.68. Now what you're going to do is when you look into the chart, the column to the very left you see a z. Those are z numbers that have the units digit and the tenths digit. And then we also can go all the way out to the hundredths place. That's along the top of our table. The 0.00 means we have a 0 in the hundredths place. The 0.01 means we have a 1 in the hundredths place. 0.02, we have a 2 in the hundredths place, and so forth. So the number 1.68, we're going to look for 1.6 in our table, and then we're going to scroll along the top to where we see 0.08 for the 8 that is in the hundredths place. And we're going to find the intersection of those two, and that is the probability that z will be less than 1.68. And since we know that the probability at any one particular value equals 0, the probability that z is less than 1.68 is exactly the same as the probability that z is strictly less than 1.68. So whether we see less than or equal to or less than won't make a difference.